Hi everyone. Our report is on the game theoretic approaches in evaluating multi-agent learning environments. Our team is UG7 from CS4246. I'm Charmaine and my teammates are Jia Tong and Joycelyn. So we will begin by giving a brief introduction and background to our report scope before going into the review of the three papers and following with our evaluation based on the predator-prey scenario. Multi-agent reinforcement learning, or MARL in short, has found incredible success in strategy games in recent years, and is becoming increasingly relevant in solving real-world problems. In our paper, we focus on evaluating the agents in an MARL context. In a complex environment, we can leverage upon game theory to explain cooperative strategies and the rationale behind decisions taken by ML agents. This is especially important in many applications of MARL that require ethical and responsible artificial intelligence. I'll first give a brief overview of the three papers. Each paper introduces a game theory solution concept to explain the rationale behind decisions taken by models and propose how we may quantify and evaluate agent contribution. The first paper studies Shapley values in quantitatively evaluating agent contribution. The second is on alpha rank using Markov-Conley chains, and the third, beta Shapley, measures the change in model performance when the datum is removed. For the first paper, we'll be discussing the concept of Shapley values, the use of Monte Carlo approximations, as well as the application of the reformulation on the predator-prey model. From this, we'll be able to address three research questions. One, if Shapley can determine how much each agent contributes to the global reward. Two, if the proposed MC-based algorithm can offer a good approximation. And three, what might be the best method to replace an agent missing from a coalition. To begin, we first define a multi-agent learning environment. Specifically, for a cooperative environment, interactions between agents during the training process can often yield better results than isolated training. This gives rise to an interesting concept brought forward by G. Hardin, whereby if one agent in an MARL uses slightly more resources, this might be inconsequential. But many agents doing so can result in the common pool of resources being exhausted. The tragedy of commons suggests that inequity aversion may improve intertemporal social dilemmas. Next, we can define the Shapley value, which is a measure of contribution to the global reward. More specifically, Shapley is the expected marginal contribution of one player after all possible coalitions have been considered. In the formula below, we can define each coalition as a subset of the original n players, with the expected sum of payouts within a coalition subset being mapped to the function v. But the problem in computation of true Shapley is that it faces exponential computation cost. For n agents, computation of Shapley value for each agent would take an average of 2 to the power of n minus 1 coalitions, and we have to further sum across all n agents. Even when optimized to solely calculate unique coalitions, the computation time would still scale at 2 to the power of n. Such computation time is further compounded by the stochastic nature of RL environments, which require sampling across multiple episodes. And for larger settings with multiple agents or features, the value of n will be much larger. For example, on the right, we have a simple environment with 3 agents and a visualization of all unique coalitions, which is 2 to the power of 3. Hence, a reformulation of Shapley value is proposed by using Monte Carlo approximation. What this formula suggests is to map only a subset random coalition of all agents to the global reward. Thus, in the formula we see on the slide, instead of summing across all coalitions, we are summing the marginal contribution obtained from a sample episode of a random subset of players. We do so by measuring the difference in excluding or including a specific player in the coalition. In this equation, instead of the original n times 2 to the power of n minus 1 coalitions, we now have a smaller subset represented by m. This implies that the time complexity can be reduced to big O of m, thus palliating the original high overhead. So in the equation last shown, we mentioned about coalitions of players. In Monte Carlo approximation, there are 3 strategies to substitute the agent excluded from any particular coalition. The first is replace, whereby the missing agent's actions are replaced by those of a randomly chosen player already in the coalition. Second is random, where we let the absent agent act simply by taking random actions. And lastly, no operation, where the missing agent does not make an action. We can then apply the reformulation to the predator-prey scenario, which is a stochastic environment with discrete action space. By default, there are 3 predators and a single prey. Predators are positively rewarded when their prey is caught. The findings were able to first establish that Shapley values of predators correlates to the predator's contribution to the global reward. Based on the graphs on the right, we can see that it is expected for faster predators to be able to catch the prey more often and hence be attributed a higher Shapley value. More interestingly, the results from running the predator-prey experiments across several iterations is able to conclude that Monte Carlo approximation of Shapley offers a close approximation to the true value. However, this is caveated by the fact that the percentage deviation will naturally seem higher for predators with an initial small Shapley. In observing the spread across all replacement strategies, which is no operation, also seems to offer the closest approximation to the true Shapley. Hence, to summarize, we are able to verify that Shapley values can yield an average metric of agents' contribution, and that the Monte Carlo approximation offers a good approximation. Lastly, no operation also seems to present the most faithful replacement strategy for a missing agent. With this, I'll pass the time to Jia Tong.
Thanks, Charmaine. Hello, everyone, I'm Jia Tong. Different from previous Shapley values that measure individual player contribution, Alpha Rank Score is introduced to evaluate the metagame strategies that involve all the players and their social utilities. We will first examine the limitations of a traditional game theory approach to finding the optimal solution for a dynamical system, after which we will discuss the concept of Markov-Conley chain, which is rooted in dynamical analysis. Then we will talk about alpha rank, which is a novel ranking metric designed for multi-agent and dynamical environments to replace the previous Nash equilibrium selection method. Lastly, some application scenarios in games like rock, paper, scissors or 3-player Q and poker will be discussed. Although Nash equilibrium can be solved in polynomial time for zero-sum games, it is often not the case for general-sum games, such as cooperative games, which maximize the total utilities. In this case, Nash equilibrium selection will often be intractable, and there is also no guarantee of a solution that can converge to such a single optimal equilibrium point. Markov-Conley chain is a concept rooted in dynamical systems. When applied in a game, it is essentially an irreducible Markov chain from which we can compute the most likely states to be the optimal states. It takes an evolutionary point of view and ranks the least transient strategies in the highest places. There are 4 steps for alpha rank estimation. Firstly, we construct the payoff table from game simulations. Recall that games are run in multiple rounds to study their evolutionary behaviors. We may use Monte Carlo simulations to build the payoff tables, which are discussed in more detail in the evaluation part. Secondly, we compute the transition matrix, which contains the probability of the agent surviving till the next round of the game. Note that agent here refers to each game strategy, which includes the global behavior of players. Thirdly, we compute the stationary distribution of each game states from transition matrix. And lastly, compute the rankings of agents from probability mass function of the stationary distribution, which indicates the expected number of game rounds each agent survives. Let's now talk about some concrete examples. Rock, paper, scissors is a classical symmetric zero-sum game. Thus, for each player, no matter what the action is taken, the sum of the utilities of 2 players will always be 0, and hence the 3 actions taken are equally optimal. Another example, Q and poker is an asymmetric multi-agent game that results in more complicated game scenarios. The strategies that specify each player's action to take are ranked as shown on the right table, where in the Markov chain visualization on the left, the optimal strategies or states are colored blues to denote that they are the most likely states for other states to transition into, or evolutionarily, they come out to be the least transient states. Next, Joycelyn will introduce our third paper.
Thank you, Jia Tong. I'm Joycelyn, and our third paper is about a unified noise-reduced data valuation framework for machine learning called beta shapely. First, I will explain data shapely, from which beta shapely is built upon. Then, I will explain the motivations behind beta shapely by analyzing the marginal contribution. Lastly, I will introduce beta shapely and its performance on 3 numerical experiments. The paper found that beta shapely outperforms state-of-the-art for those 3 experiments, which are detecting mislabeled training data, learning with subsamples, and identifying points that have the largest impact on the model. Data shapely is a function of marginal contributions that measure the average change in trained models' performance when a particular point is removed from a set with a given cardinality. This is the equation to compute the shapely value of a datum, Z star. U is a utility function that represents the performance of the model trained on a set of data points, which is D. The marginal contribution function, which is the last term in this equation, considers all possible subsets with the same cardinality and measures the average change of the utility function when datum Z star is removed. So what data shapely does is that it considers all cardinalities and takes the simple average of all the marginal contributions. Data shapely uniquely satisfies the natural properties of a fair division of rewards in cooperative game theory. Firstly, there is the linearity axiom. If 2 coalition games are combined, then the distributed games should correspond to the games derived from each of them. Secondly, the null player axiom. The amount that a null player contributes to any coalition is exactly the amount it is able to achieve alone, and the shapely value of that null player is 0. Next, the symmetry axiom. If agents I and j always contribute the same amount to every coalition of other datums, they are interchangeable and they should receive the same shapely values. And lastly, the efficiency axiom. The sum of the shapely values of all agents equal the value of the grand coalition so that all the gain is distributed amongst the agents. Next, we look at marginal contribution. From these graphs, we can see that signal-to-noise ratio decreases as j increases. In other words, when j is large, the signal of marginal contribution is more likely to be perturbed by noise. Hence, we should assign large weight to small cardinality instead of using the uniform weight in data shapely, in order to capture the impact of one datum better. So back to the 4 axioms of data shapely, the paper then showed that removing the efficiency axiom gives a new form of data value that can assign larger weight on the marginal contribution based on small cardinality rather than large cardinality. So we introduce a function called the semi-value, which satisfies the linearity, null player, and symmetry axioms. Every semi-value can be expressed as a weighted mean of marginal contributions without the efficiency axiom. The first property of a semi-value is that there must exist a weight function that satisfies this condition, so that data values can be formulated. Although the semi-value loses the uniqueness of the weights, it is unique up to the sum of data values. So any 2 semi-values are identical if they have the same sum of data values. Now we introduce beta shapely. The computation of the weight function in the semi-value can be expensive or infeasible because it contains an integral. So we propose beta shapely, which has a closed form for the weight. We consider the beta distribution with a pair of positive hyperparameters, alpha and beta. In the graph, each color indicates a hyperparameter pair. Take the blue line, where the normalized weights assign large weights on small cardinalities and remove noise from large cardinality. And the purple line is the converse of that. To demonstrate the practical efficacy of beta shapely, we conduct some numerical experiments. Beta 16.1, which focuses on small cardinalities, is consistently the best for detection, subsample, and point addition tasks, while data shapely, which puts equal weights on all cardinalities, is the top performer for point removal. Now I'll pass on the time to Charmaine to take you through our evaluation.
Having reviewed the key points of each paper, we will now briefly bring you through our evaluation. Our evaluation revolves around 3 key aims. First, to allow us to provide an independent basis of verification for some of the paper's findings. 2, to extend the application of algorithms with varied parameters. And 3, we'll be providing a conjecture and reviewing future developments in some aspects where we might not be able to justify a quantitative evaluation. So I will first re-establish the predator-prey scenario mentioned earlier in the presentation with a few defined parameters. The scenario is based on a simple tech environment where predators try to catch the prey. The predators are trained using the multi-agent deep deterministic policy gradient algorithm. The prey by default has a faster speed compared to the predators, and if the prey is caught, predators are awarded positively, which is cumulative in each iteration. The next slide presents the varied parameters for all 7 models we built. As actions are non-deterministic due to the stochastic nature, we ran 3 iterations for each model for more reliable average estimates, with the exception of model 3 due to the exponential runtime. As can be seen, some varied parameters include varying speeds of the prey and each of the predators, and episodes used in the Monte Carlo approximation. A stark contrast in our findings is in the time complexity when computing MC-approximated Shapley versus that of true Shapley. The following graphs illustrate the clear positive correlation in time complexity against number of episodes for MC approximation on the left and true Shapley on the right. Yet MC approximation is able to run at a fraction of the time. For 2000 episodes, true Shapley takes 41 minutes to run, but an MC approximation of 2000 episodes takes just over 13 minutes. Further, running models 4 to 7 using the replacement strategy highlights that an increasing M value used does indeed seem to result in a more accurate MC approximated estimate against the average true Shapley calculated. Although this finding was not fully consistent, we postulated that this inconsistency is due to the fact that when a model built for stochastic environment is based only on a small number of total episodes, this introduces a larger degree of deviation and variation in the learned rewards across iterations. Instead, from model 3, which is a single run of 20,000 episodes, the results are more parallel to findings from the paper. Across all 3 predators, the no operation strategy appears to provide a relatively accurate measure of agent contribution. Now, I'll pass the time over to Jiatong.
Similarly, we study how the number of Monte Carlo simulations will affect the probability of top rank strategy by alpha rank metric. We feed the payoff tables generated from Shapley experiments to the alpha rank estimation function. We can observe from the right plot that with the number of simulations M increasing, the optimal strategy for predators gets more confidently and reliably estimated, where the y-axis measures the confidence score. To zoom into how alpha rank ranks the strategy for a particular game, we take the example from our 7th model, which has the most Monte Carlo simulations. The game is evolving, and we use a finite number of simulations to estimate the optimal states. The table on the right shows for each strategy the global behaviors of the 3 predators. There are 3 states ranked with the highest probability to be the optimal states, and they are showing the Markov chain with the blue colors to denote that they are the most durable states from an evolutionary point of view. Next, I will pass the time to Joycelyn.
Thank you, Jiatong. Moving on to beta Shapley, recall that it can effectively identify helpful or harmful data points that affect model performance. To tie this in with our work on evaluating agents in the context of MARL, we conjecture a similar measure that can evaluate how variations to a multi-agent environment can affect model performance. To do this, we can factorize the variations in the environment and evaluate each factor's effect on the result. This can then be used to evaluate the robustness of the model in unstable environments or evaluate the importance of each environment factor. Both Shapley and alpha rank come with limitations. Firstly, the presented MC approximation framework of Shapley cannot measure contribution simply based on a specific episode or precise action taken. Secondly, based on a stochastic environment and non-deterministic agent behavior, direct comparison between the global rewards learned from different models is not possible. And lastly, based on our modeling, results from several iterations of the same model still give rise to a level of deviation from the true Shapley. At best, multiple iterations across larger M episodes used in approximation may offer a more reliable comparison with lower standard deviation. Game theoretic approaches in MARL can be extended beyond games and into other applications of MARL, such as autonomous driving and robotics. Additionally, it can be applied to study social sequential dilemmas to provide insights into societal issues in the field of economics, policymaking, and sustainability. The computational feasibility of Shapley and AlphaRank, coupled with the insights from evaluating variations in environmental factors, can serve as tools to engineer robust AI models in future. We have come to the end of our presentation. Thank you.